Let's begin. We will continue where we left off last time. But before doing that, so there's going to be a lot of coding today, and then we will also talk about, we'll start on advection. And, hold on, full screen. So we left off here last time. We did upwind, etc. And what I want to start, I know I skipped this slide last time, but I think it's important to see how it's implemented, because you will have to do that when we get in 2 dimensions. So before we move on to diffusion, I want to revisit this question, and we will do Berger's equation on that, where we have 2 opposing velocity fields. But even before that, I want to share with you the animation script. So on your canvas, if you go on Canvas, Files, Python, so on your canvas, under Files, Python directory, there's an animation example script, okay? It might work on your computer, or it might not. If it works, great. If it doesn't, look up what the error is giving you and try to download whatever is missing. My guess is that it should work straight out of the box if you have all the video tools installed, the FFmpeg, which is should come built in with Python. I know on Macs it should come in by default, it should be installed. But if not, whatever error gives you, Google that or throw it at GPT, and it will tell you what you need to install. So then, at least for next time, you'll have that up and running. Okay? So it's not necessary right now to do it. But for the homework, I will want you to do animations, because that's the best way to visualize time, is to animate it, right? So let me show you how that works on my end. I have to be super careful with this HDMI cable today. Okay. Did you find the script? Perfect. So what I will do, this is what we were doing in class last time. Window, move here. Oh, good grief. Okay. So I'll zoom in a little bit for those in the back. And if you see the script, on. Let me copy it from on my end. Okay, so paste the script at the end, in an extra cell at the end, and we're going to come here. We're going to run this again. Okay, so this was the whatever heavy side, etc. And we did all of this, and it animated it. So at the bottom, just paste whatever I have here. Okay. So I can explain to you what I'm doing. With the animation, there are a couple of ways to do animations in Python, or 3 ways. You could dump a figure, save a figure, so loop over all the times. For each time, make a plot, save the figure on disk, and then go use an external tool to animate those images. Oftentimes, this is the cleanest approach. It gives you the best quality. It's faster, reduces memory load on Python, etc. So I do that for more professional work. For quick things like this, because that other one, it needs built-in tools. On Windows, they're going to be different than Mac. On Mac, I use FFmpeg, and one line, I can just animate the whole thing. But for the intents and purposes here, we will just use built-in Python. There's 2 approaches to do this in Python, and one of them is called function animation. And that's the one that I recommend using. There's another one, artist animation, which this is better for what we're doing. This is better for plots. And what it essentially does is you give it a function that updates a plot, and you give it a number of frames, and then it goes and iterates over those and just plots them and saves them and automatically converts them into a movie. Okay? So it's going to do that automatically for you. Now, what I'm doing here, I'm porting the animation toolkit from matplotlib.animation, and I'm creating an initial plot. I need to create a figure and a plot in there so I can update those data. Because if I create a new plot every time, it's not going to make it work. It's gonna wash everything out. It will not work as cleanly. So I create initially a figure, and it's X, I call it, or call this plot. And plt.subplots, if you don't give it any numbers here, it's just going to create one figure, one plot. And then I plot my initial condition, because that's my starting point. And I store it in something called curve plot or my plot, whatever you want to call it. Now, what I will do next is I will modify the data in this one. Okay, what I will do is modify the data in this one. Then I set a few things that I want my line style to be dash dot, and my plot limits. You want to fix the limits because you don't want it to automatically update the limits. Then your animation is going to look weird every time your y-axis is going to change, your x-axis might change. So fix the limits, and I went from 0 to L on my x domain. On the y limit, if you look at your initial condition, it goes from 0 to 1, right? So I give it a little buffer, about 10-20%. So I go to about 1.2. If you see that here on the y limit. And then my function update that does the animation is going to essentially loop over each frame, which is each time step in my solution, in my time solution. And for each time, grab the data along the x-axis, right? So this is time t, and if I put the semicolon here, it's going to give me all the points on the x-axis. And then I will update the data on my curve plot that I created here. So I'm still referencing this original plot, but I'm telling it clean up the y data and put the new data in it, and then update. And when you do this, it does the animation for you, and then you would need to save it. Now, this save line took me a while to figure out, so keep it as it is. The problem you might face is you might not have any of these installed. If they don't exist, just delete this extra argument. You might not get a very high quality animation, but if it barfs at you, if it crashes because of these, just delete this extra args and keep the other ones, okay? And if you run this, it should just work. And what it will do, so look at the star here, it's still working. It will take a minute. It's a memory intensive operation. And so it will take some time. Oftentimes, you don't want it to. Okay, so I'm going to move this to the right. Let me see. Okay. So let me show you. Did you try it? Did it give an error? Did it work?
I mean, these tries didn't work, and when I gave it to them, I got
an error. Yeah, because you probably don't have FFmpeg.
That's right.
Yeah. So you would need to install that. If you do conda install ffmpeg, it will figure it out. On Windows, it's a little bit more complicated. If you're on a Mac or Linux, it should just work out of the box. Did it work for anyone? No one? No one. Okay, what if you, okay, so you probably need to do conda install ffmpeg, and that will fix everything. So if you go on your terminal, if you have a Mac, on Windows, you'd have to go to the Anaconda Navigator. Okay, and just do conda install ffmpeg. Okay, I don't know of an other writer, but what this will do for you, it will create a file with the animation inside it. Let me see. Test. So this is what I got here. Oops. Okay. So this is what I have here for this animation. It starts decaying as expected, right? And I put that line on top to put the initial limit and see how it's diffusing. Anyway, so if this doesn't work for you, we can that's the tricky part of this, is that it's not universal. You have to figure it out on your own computer. I tried, but my guess is that if you install ffmpeg or look for another writer that might be installed already on Windows or on your machine, it will just work. ffmpeg is the best. Did you try, Elizabeth? Did you try do conda install ffmpeg? Okay. It's loading, yeah. It's good. So try again and let me know if it ends up working. For those who are on Mac, just go on your terminal, say conda install ffmpeg, and then yes, it will install everything. If not, You'll have to some Googling to do. Okay, well, I tried. Sorry it didn't work. That's the tricky part with Python. I have to find another way to do this nicely. Okay. Let's come back here. So when we did upwinding, we needed to know the direction of the velocity. Okay? If the velocity is moving from left to right, we do a backward difference, and if it's going from right to left, we do a forward difference. When the velocity is constant throughout the domain, it's not a problem. You pick one or the other. But in practice, the velocity is going to change throughout space and time as well. And so you need a way to automatically switch without having to do a lot of, you can do if statements. You can say over every point, they give me all the positive velocities, negative velocities, choose this or choose that. An if statement is going to be inefficient and it will break a loop, okay? So a cleaner way is to just pre-compute this as I explained to you last time and assume that the velocity could either be positive or negative, and if you implement these formulas, it will automatically do it the correct way, okay? So what we will do, we're going to go and revisit our problem here. Okay. So in this problem here, we were upwinding, okay, because we assumed C is positive. But if I give a negative C, it's going to crash, okay? So if I give a negative C, it's going to crash. I'm run it, and I put a negative C, it crashed, okay? Because, and look, it's like 10 to the power 88. It doesn't make sense, obviously, right? So what we needed to do here, if C is negative, we needed to do upwinding on the other side, or downwinding, essentially. What it's doing here is downwinding, but on the wrong velocity. So let's go ahead and implement the fancy way of doing this. And let's see the formulas. I'll move my keynote. So from here onwards, you will assume that you have a variable velocity field. So I need to compute these quantities, C plus C minus, and these two, and then blend them together. And then it should just work regardless of what your velocity is, okay? So for here, let's implement this. And look, this could work even if C is a vector, is a field, not a constant, okay? So let's do this. We'll do C plus, okay, fancy version of upwinding works with varying velocity direction. Okay, so we do C plus is equal to 0.5 times C plus NP dot absolute value of C, and then C minus is 0.5 times C minus NP dot absolute value of C, and then the backward difference, backward difference, so that's du by dx, assuming there's backward, it's equal to C plus times u, so that's upwinding, minus np dot roll, sorry, phi, let's put phi because that was our dependent variable, phi minus np dot roll phi, and then we set shift equal 1, so that's upwinding, right? So that's this formula. This is the backward difference over here. Next, I want to do the forward difference. And then forward is C minus times NP dot roll phi minus 1. So that's phi I plus 1 minus phi. Okay, and then finally, my right-hand side is equal minus backward plus forward, because that's going on the right-hand side, agreed? So advection is minus C d phi by dx. So it's going to have a negative sign regardless of the sign of the velocity, okay? And over delta x, right? Over delta x. And then, so now this should just work with this one, right? C is negative. What happened? T eval is none? No. Okay, let me run this again. C minus, C minus, backward BKW RD, and forward, forward. Okay. Okay, so now it's working, and it's moving in the other direction, so I'll run the animation. Yeah, I'll keep this here for a second for you to see it, and I'll run the animation again. Okay. What the heck? Let me try what happened to the animation. Test.mov. For some reason, it didn't complete the animation. I'm going to try it again. Okay. Anyway, so you will need this moving forward. I recommend you just keep this everywhere you're working with advection. There are some cases we might see later where advection, okay, it's right here, test. Okay. Where advection, you can do central on advection if diffusion is very, very large, if physical diffusion is large. Okay, so you see how it's moving. Now it's moving to the left and circles, going through the periodic domain. Okay, great. I had an example of Berger's equation here. So Berger's equation had a nonlinear velocity term, a nonlinear advection term, which is u du by dx, because then the velocity depends on the dependent variable. There's two versions of the Berger's equation, and the Berger's equation is used as a simple model of Navier-Stokes of fluid dynamics. It has a nonlinear advection term, and it has a diffusion term that looks like what we will call later the stress tensor. Okay, but this has diffusion in it. We didn't do diffusion yet. A special version of Berger's equation is the inviscid Berger's equation, which is this guy without the diffusion term. And what it does, what I claimed it does, is it generates, it can generate shocks, right? It can generate shocks. So we can test this as well, if you want. So let's go ahead. I'm going to duplicate this file and do one for Berger's. Oops. Duplicate. So go ahead and duplicate this file, because we will reuse the code. I don't recommend you keeping all the code in one place. I mean, it depends. We will need to change the right-hand side in this one. So this is in class, inviscid Berger's equation. In class, inviscid Berger's equation. Let's put in a post. Well, it won't allow us. Inviscid Berger's equation. So in this case, we can do the Gaussian or the Heaviside. What I would want in this case is an initial condition where u, the dependent variable, changes sign, right? So that I can have one side of the domain things moving from left to right, and on the other side things moving from right to left, okay? So I need a sine wave, like I explained last time. So we could probably do, let me see what I did here. I did a sine 2 pi x. Okay. So now for this one, I need to change this. This is no longer advection right-hand side. This is Berger's right-hand side. I'm going to call my dependent variable u. And I don't need an advecting velocity anymore. Agreed? Because the advecting velocity is already given to me by the dependent variable. So I'm going to clean this up here. I don't need it anymore. And then what I would replace here is C plus. This will work for arrays, not just a constant. That's why I used numpy.absolute, not just Python's absolute. And then backward. So that's going to be your dependent variable. Everything is u forward. Everything is on u. Okay, that's it. That's all we need to do to convert this into a burger's right-hand side. Okay, and then my initial condition, let me see. For my initial condition, let's see, let's do it. Let's just do it right here. But I need to comment out the solve. And then, let me see, IC initial condition is mp.sign, let's say 2.0x. Okay, and then we can plot it, plt.plot, finish x, initial condition. It's this one here. Okay, and then plt.grid. Okay, so this is my initial condition of the dependent variable u. This is positive, this is negative. What's the advecting velocity? It's u, it's those values. So on this side, this piece is going to move to the right. On this side is going to move to your left. What will happen? They're going to collide with each other and start forming a shock wave. Okay? In 2D, this will start spinning because you have another dimension to move the flow through. Okay? It will start spinning. But right here is going to create a shock. Once you create a shock, the equation just has a different behavior. You're going to start seeing it decay, and it has some other condition that we would worry about. So, okay, I'm going to solve IVP. All right, I solve it. Name advection right-hand side is wrong because we have burgers. Not burgers equation. Burgers. Did I not execute this? Burgers, right-hand side. Takes 3 positional arguments. Yep, I don't need to pass the speed. What did you say, Parker?
The very first line on the right-hand side of B.
Pardon me? Oh, yeah, that's correct. You don't need this, but I like to do it to make sure I'm starting with clean memory. Good catch, Parker. Thank you very much. Okay, so we did the solve. And then we can plot here my initial condition. So my initial condition. And then the last value of the burgers equation. Okay, so the initial condition on the burgers is in black. That's the first time step. After 2 time steps, right, you start seeing this side move to the right and this side move to the left. It just works flawlessly. This is a varying velocity field in space, okay? It's a varying velocity field in space. Okay? Can I keep this one open? No, this one. Keep it open, please. Okay, and if you run the animation, I showed you the animation last time. I can run it again over here, and let me call it burgers in class. Okay. Let me see. Burgers in class. Okay, I need to adjust the limits from minus 1.2 to 1.2 and run the animation again. Okay. Okay. See what it's doing? And then the decay here is shock wave behavior. There's some energy dissipation that happens in this case because the conservation law is no longer satisfied once you are discontinuous in this case. So it does dissipate this way. That's the mechanism and the pneumatics do capture that mechanism, interestingly. But the point here is that this will work with the full upwind will work with this formula. Who was that guy? Hello. Come on in. Okay. All right. We talk about diffusion next. The great equilibrator. I showed you this cool animation last time where I put a compartment, I put particles on the left side, and almost equal number of particles, and I let those particles, I just took steps, and every step I randomly told the particle to either move left or right, 50-50 chance, uniform, equal chance. And so you see here, some of the bins are going up, sometimes they go down, they go up, but there's a general trend that they move from the high concentration of particles to the low concentration of particles. So that's diffusion. For the way we observe it macroscopically, or the model we make, the simplest kind of what we call normal diffusion. The other that's not normal is called anomalous diffusion, which is different kind of model for diffusion. We'll learn some more of that in mass transfer. But the standard Fickian diffusion, normal diffusion, Fick's law, results in this equation. Remember, the diffusive flux is minus k grad phi. This second derivative is the divergence of that, minus the divergence of that, right? So diffusion is not a second derivative. It does end up showing up as a second derivative, but the diffusive flux is minus k grad phi, and the minus sign is to enforce the idea that we're going from high value to small value, because the gradient points to the high value, so we want to flip that sign. And the divergence of that, and in 1D, it becomes the second derivative, so we saw this. Now, the approximation, the approach we follow numerically with this is the same as we did with the advection, except here we have a standard central discretization for diffusion. And if you remember when I talked about the Laplacian, this is the 1D version of the Laplacian. I told you the Laplacian, what it's doing is trying to average things around a point. If you go back, we did that numerically. We said the average at a point is essentially the value at a point is the average of all the neighboring points. And this is what it's doing. And that makes sense because diffusion is trying to equilibrate everything. If you are at a peak, it's going to lower that peak. If you are at a valley, it's going to increase that valley to make sure everything equalized. And we convert this semi-discretely into a system of ODEs. So this is a system of ODEs at all points I, except the boundaries. We'll do something else, something different at the boundaries. So we follow the same approach with numpy.roll. And we don't care about the boundaries because we're going to go and fix them later, right? So that's the cleanest way of doing this. That's what's so neat about this, is you do the roll on the whole thing. And phi I minus 1 is roll shift plus 1. Phi I is just phi I. And phi I plus 1 is numpy.roll and shift minus 1 over delta x squared. You're done. We have our right-hand side built, okay? So we're just going to go and implement this. But we need to talk about boundary conditions first. With diffusion, it doesn't make sense to use periodic boundary conditions because diffusion needs to have something fixed at the boundaries. Okay, it doesn't. With advection, it makes sense to have a periodic domain because you're moving, you're going to run forever. Diffusion is sort of a stationary thing within the confines of your system, right? So you need to define the boundary on that system. We can do it with periodic, but it's not going to give you a lot of information because with diffusion, if your boundaries are fixed at zero, eventually everything is going to decay to those boundary values. So that's a great check that we will need to make. So we cannot use boundary conditions. We will use Dirichlet conditions for diffusion. We can use also Newman conditions, which we will implement later, but we'll start with Dirichlet because they are the easiest. That's what you did in your homework, what, 6 or 5? One of homework 6, I think. That's exactly what you did. So again, we are after finding, the question is, this is a solve IVP solves a system of initial value problems. We need an ODE at every physical grid point. We need to figure out what the ODE is at the boundary points. If the boundary is a Dirichlet condition, how can we convert that to an ODE? Well, it's kind of really straightforward. If you are given a value, a fixed constant value, let's say at the boundary, so phi at the boundary for all times is constant, then what is the ODE that will give you a constant? Is d phi by dt equals 0. Because the solution to this ODE is phi equal a constant. How do we set that constant? Initial condition. We need to make sure that at the Dirichlet boundary, this is my ODE, so my right-hand side is going to be 0 at that boundary. But I need to make sure that my initial condition is what? Is this value exactly. Okay, so we are tricking solve IVP to converge to this solution. And we'll do it in one step because this is a trivial ODE, right? It will integrate it in one step. Immediately you'll have that implemented. And you already have your initial condition at A, so you're not losing, you're not messing with your numerical solution at all. Isn't this cool? Like all we have to do is just think of it as ODEs, right? Just ODEs. Now in your homework, I might give you A cosine T. You're going to figure out what the ODE means in that case, right? And put the initial condition correctly so that you evolve that boundary condition properly. Just think, what is the equivalent ODE that I have at a Dirichlet boundary? Okay, with that being said, we are going to revisit our same problem. So we're going to duplicate our advection file, and because we already have the initial conditions, and we will diffuse this guy and that guy, and we'll put zeros at the boundaries. So we initially have 0 everywhere here. So we'll just put zeros at the boundaries for Dirichlet, and then we'll see how things diffuse. Okay? So let's do it. All right, so let me first duplicate. I said I'm going to duplicate the linear advection file, right? I'm going to duplicate that, and I'm going to call it, I'm going to move it here, and let's call this, so that's the third exercise we do in class. Let's do 2025 actually. In class, diffusion equation. Let's solve IVP. Okay, I still have my Gaussian, my heavy side, but now my diffusion right hand is going to be a diffusion right hand side, and this remains the same. But now I need to do everything central, and so what I will do is my right hand side is equal, and we said we have those the roll, the numpy dot roll, right? So, okay, but first, yeah, I'm going to keep this phi, and I need a diffusion coefficient. I'm going to call it k. And what I have here for my right-hand side is k over delta x squared over dx times numpy dot roll. And we will do phi I plus 1 minus 2 phi I plus phi I minus 1, correct? Or phi I minus 1 minus whichever you like. And numpy dot roll of phi and shift is equal to 1, so that's phi I minus 1 minus 2 times phi plus numpy dot roll phi and shift equal minus 1, correct? Now that's going to put stuff in the right-hand side at the boundary, but I don't want it to. I want my right-hand side at the boundaries to be 0 because I have Dirichlet conditions, okay? So Dirichlet at both boundaries. And then my right-hand side at 0 is 0, and my right-hand side on the other side of the domain at minus 1 is also 0. See what I'm doing here? I'm saying my ODE at the boundaries is d phi by dt equals 0. Everywhere else is d phi by dt equal k delta x phi I plus 1 minus 2 phi I plus phi I minus 1. Okay? Let's just set my ODEs at the boundaries. I need to make sure I fix the initial conditions. Okay? I need to make sure I fixed my initial conditions correctly. That's it. That's it for diffusion. So I'm going to erase this too. Okay. Now here I am doing, okay, let's start with the Gaussian initial condition. I'm going to comment this out a little bit. I don't have C anymore. I have a diffusion coefficient. So just do 0.01, and L, just keep it 0 to pi. And we can plot the initial condition to check things. plt.plot x initial condition. It's this guy, right? Now, it looks like it's 0 at the boundaries, but I'm not going to take any chances. What I will do here is IC at 0, I'm going to enforce that value equal 0. And IC at -1 is also 0, because I'm putting 0 at both bounds. I can change the value. We'll change it later, and we'll see how it will diffuse to that value, OK? So make sure here, enforce Dirichlet at both boundaries, or at the boundaries, OK? All right, so we are ready to solve this. And we can run it. It gives me an error because, my argument, I need to pass k, and over here I need to do diffusion right-hand side. Okay, wow, it solved it. Okay. So down here, oops, I'm going to plot my solution. And the array object is not callable. Oh, I see here. OK, so that's my initial condition and my initial time step. Then take one time step. It's doing something after 10 time steps. Oh, look at that. It's starting to come down. So my numerical solution is in red. Starting to come down, starting to bump up over here a little bit. And then if we go like 30 time steps down, it continues diffusing like this. And then all the way to my T final, it went to this point. My T final was 10 seconds. I could do 30 seconds, let's say. And 30 seconds, it just didn't continue diffusing as fast. It just kind of started slowing down. I can do 50 seconds. It's really, really slow. It's going to continue diffusing to reach 0 very, 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 very slowly. OK? Who's not in sync? Would you want me to scroll up? Where are you at? OK, you want me to scroll up? OK, take your time. Copy. If you're done copying, go ahead and experiment with the solution. Try to change the Dirichlet condition. Put the right at 1, for example, and see what happens. It's going to try to climb up to 1, and you'll have a straight line profile from 0 to 1. Yeah? Pardon me? Here? K over dx. Dx is defined here. Phi is passed on as an argument. Here? No. You don't pass it as an argument. This is solve IVP. Remember, it's internally figuring. So by definition, the right-hand side function, you don't pass time or the dependent system. The right-hand side function for solve IVP is always, the first two arguments are time and the array of dependent variables. So you don't pass that. That's what you're trying to find, right? It's not like a known argument that you pass. That makes sense? Yeah. Mm-hmm. No, it's just easier for me than having to type 2 stars to the power. It's just easier. Yeah. In the past, there used to be some advantages to doing divide versus a power, because computing a power numerically was, on a computer, was more costly, but that's not the case anymore. So, yeah. You guys get a solution? Okay, what happens when you change your Dirichlet conditions? You put 2 or 3, it goes up, right? Mm-hmm. Or you can put a negative value or whatever. Well, if this is temperature, it doesn't make sense to put negative value. So let's do Dirichlet 1 on the right-hand side. And then what's going to happen, look at that. It's starting to climb up to that boundary condition. This is super cool. Okay, and I can do an animation here and go from 0 to 1.2. And then I don't need this. Sorry, you can't animate yet, but diffusion test 1. And I'll animate it so that you can see exactly what we're doing. It's taking a long time because it did a lot of time steps. And you can control that by specifying an evaluation time. Okay, so remember here I'm using RK45. RK45 is an explicit method. And from your homework assignment, you should have observed that the system becomes more and more stiff as k increases. That's a property of diffusion as the diffusion coefficient increases. And so no wonder RK45 has taken a lot of time steps. And to check that, I can do len of sol.t, and it did almost 1,600 time steps. So if I were to do BDF, it's going to do 78 time steps, right? So be careful, though. Don't just go and use BDF randomly. If I were to reduce my diffusion coefficient to a very small value, like 1e to the minus 5, okay? Well, BDF did it in 21 steps. That's fine. But RK45 did it in 7 steps. So because it's less stiff at those small, very, very small diffusion values. But obviously, as the diffusion coefficient goes up, then look at RK45 is going to struggle a lot. And in fact, that's a bad idea here. So I'm going to stop it. I'm going to go to BDF. And then you can just figure that out real quickly. And it diffuses it very, very quickly. It diffuses the thing very, very quickly. So 10, 30, let's say, and then 50. And then it just diffuses it really quickly. OK? But that's diffusion. All right. So let me move this to crest on. Here. Okay. So that's how it's diffusing. It's trying to equilibrate. Very nice and smooth. It smoothes everything out. It's super cool. And you heard me say a little bit ago, nobody asked me about that, but you heard me say that sometimes you are OK to use central on advection if there is diffusion, physical diffusion. It's because of this. If advection central is going to cause wiggles, but you have physical diffusion, what is diffusion going to do? Oh, wiggle here. I'm going to smooth it out. Okay? But it depends on the strength of diffusion. Okay. All right, so let's do the heavy side. Again, the heavy side is going to look almost similar. We'll do heavy side, and I will go back to 0 over here. And let me do a t-eval mp.lin space. And so I'm going fast here because I trust that you guys, this has been beaten into your heads. You know what we're doing here. You did it with homework assignments. You did it on your project. So you know I don't have to go and re-explain again what I'm doing here. And if not, you got to catch up with this. Okay, so to t-final, and we'll do 100 time steps to plot this at, and I'll do t-eval equal t-eval. Okay, so that will force it to do exactly the number of time steps I want. And this one already diffused everything pretty quickly. And diffusion coefficient is 1 here. Let's do 0.1. Okay, and let's do a little animation. So this should go faster because just 100 time steps. Okay, so I'm going to move this over here. See how it diffused real nice and quick. But then you will notice that, okay, I need to show you what it does in a single time step. So I'm going to come back here and take just a single time step. And actually, I'm going to take a smaller time steps to see the behavior happening at the beginning of the solution, because I'm going to ask about that in a minute. So notice here, when we did the Gaussian already looked like this, and it just, all of it decayed together. But when I had that sharp signal, it didn't fall down from the peak, but what happened at the corners, the first thing that happened is that the corners got smoothed out. It's like diffusion acted faster on those corners than on the rest of the signal. Once everything was smooth, no sharp edges, then it continued decaying everything at the same rate. Okay? So there's a reason for that that we will investigate in a little bit. All right, so what did we observe here is that, what do we observe here? What did we observe? Okay, what did we observe? Well, just kind of what I said right now is that two things. Diffusion is generally stiff. The larger the diffusion coefficient, you have to be careful. You might want to switch to you have to switch to an implicit solver, BDF or Rodau. Okay, you have to switch. Okay. Now, if you have a mixed diffusion coefficient, in some regions it's small, some regions it's high, your entire system is still stiff because that's the bottleneck. Okay, so you need to go to a implicit solver. But if your diffusion coefficient is small in magnitude, then you can use an explicit solver. You're okay. And you can tell it's taking so long. It's probably very stiff. It's taking a lot of time steps. That doesn't make. I need something faster. The second thing that we observed is what I said, is that with this Gaussian pulse, the whole thing kind of went down together, nice and smooth. But for this one, what we notice is that wherever there's a sharp step or sharp gradient, the gradient from here to here is infinity essentially. It's just making a 90-degree turn, right? So it acted on those first. It smoothed those out before it started decaying the rest of the signal. Okay? So what is going on? That's true. But to dig a little bit deeper, the next thing we want to do is instead of diffusing those crazy signals, the Gaussian and they look innocent, but they are complex in the sense from an elementary function perspective. A nicer way to think about this, and you'll see how this is going to be helpful, is if we diffuse a signal that looks like this, a baseline sinusoidal signal, maybe just one cycle, okay, plus an additional signal on top of it with some different frequency. Okay, so let's see what happens. Let's see what happens. So we will continue with this one, but now I want to experiment with this sine x signal. So I'm going to do here define. Actually, let's just do it down there. Let's just do it down here. Okay. Instead of this IC, I want to create mp.sine x plus, let's say, 0.1 times mp.sine 2x. Let's see what happens. I want to plot this first. I want to see what happens. Okay, and then the initial condition is 0 because the boundaries are 0 anyway. So I'm satisfying everything correctly. Okay. Well, okay. Let's do mp.sine. Keep it sine x plus 0.1. Okay. Let's do 10x. Okay. Let's do 30x. Or actually, let's do 10x. Okay. So what I did here, it's almost I perturbed this this initial signal, and I added some small oscillations on top of it. Okay. We can reduce the size of those if you want a little bit, maybe 0.05. See what it looks like, or keep them at 0.1. Let's keep them at 0.1. Okay. Okay, so let's see what happens. I'm going to run this I'm going to fix my diffusion coefficient, k equals 0.1, and I'm going to run this for a small time because I want to see this initial behavior. So half a second, I want to see what's happening initially, and I'm going to keep BDF, okay, and I'm going to run this. Okay, so let's do the animation first. Diffusion test, lambda diffusion of sinusoidal, lambda equals 5. Okay, so we can trace what's happening. Okay, so let me see what happens here. Perfect. So I'm going to run this, move this over here, move to Creston. What do you see? Okay. Okay, let me plot my, so the initial sine wave was almost like this, right? The initial sine wave was kind of behind like this, right? Now look what happened. What did it do? What did it diffuse first? What part of the signal those corresponded to? So my signal, come on guys, sine x plus 0.1 sine 5x, or sine 10x. The high frequency, it diffused the high frequency signal before it diffused the low frequency signal. Okay, so let's verify that further. I hope you're understanding what I'm doing here. Okay, where is that? That's not Berger's equation. It's not this one. It's this one, right? Okay. So let's do sine 20x. Okay, so that's my signal, right? That's my signal. And I solved it, right? I'm going to animate this, and I'm going to do sine, this is lambda equal 20. So I have a main primary signal, okay, like almost 1 hertz, and then I have a 10 hertz frequency on top of that. Okay, what do you think is going to happen next? Okay, same thing that happened with the previous one. Look at that. It kills the high frequency first, and then dissipates the remaining lower frequencies. So it seems that from just observing this, we can start forming a hypothesis. Okay, so think about a hypothesis while I bring the slides back. Okay, what would be our hypothesis in this case? Hypothesis is that diffusion okay, especially for the PhD students. If you cannot formulate a hypothesis from seeing some information, you have to think about that. What could be our hypothesis here? We just saw that, yes. Well, you're not a PhD student. Okay, Parker, go. Is limited by the lowest frequency. Okay, or, and the opposite is also true, is that diffusion tends to diffuse the high frequency signals before it diffuses the lower frequency. So it seems that the rate of decay in diffusion is somehow proportional to the frequency that the diffusion is acting on. Now, everything is frequencies. Everything is a bunch of frequencies. So when you go back to that Heaviside function, what's going on at the corners? If you decompose this into a Fourier series, the corners have thousands and thousands of very, very, very high frequency signals so that you're able to build a sharp interface. So the reason it acts there, diffusion diffuses those first, is because of the presence of the very high frequency signals there. It diffuses those first, and then it continues with whatever is left. Okay? So you have a hypothesis. How do we test it? We have some observational evidence from numerical calculations. It's a test, but it's not a proof. A true proof, you need math for proof. So let's try to prove this mathematically. Thankfully, this is a linear equation. And whenever you see, so we can solve it analytically. And whenever you see second derivatives in an ODE or PDE, if you remember your ODEs or PDE, whenever you see second derivatives, you immediately think sines and cosines. Why? Because first derivative of a sine is a cosine, the second derivative is a sine. So if you start with a sine, second derivative is going to get you back to a sine. If you start with a cosine, second derivative is going to get you back to a cosine. Okay, so we will use this to our advantage, that the solution to this equation must be built on sines and cosines. It's so amazing that, and that's tied in directly to the sine and cosine frequencies, because the diffusion solution itself is always built on sines and cosines because of that second derivative. Okay, so let's see how this works. So suppose, okay, the other thing, it seems that the decay in time doesn't care about location. It's not like it's decaying faster over here than over there, as long as the diffusion coefficient is constant, where it acts at the same rate everywhere. So then you can argue that this is actually the product of something in time that's decaying in time times, I'm going to start with this. I'm going to assume that my phi, my solution, looks like, a sine times some function of time. Why the sine? Because there's a second derivative. If I plug this back, if I plug this over there, and the second derivative of this is going to give me back a sine, so I can have equality in those. So that's the reasoning about choosing the sine or a cosine. This will apply for a cosine, as we will see next. Okay, so I'm asking, what happens if I assume that my solution looks like this? F of t, because it's decaying equally everywhere in time, it's independent of space, so it's a function of time acting on everything in space, so it's a product, right? Then what happens if I substitute this over there? What I will get is f prime, so df by dt, d phi by dt is f prime times sine lambda x. And on the right-hand side, I get minus k lambda squared, because I differentiated this twice. First derivative is cosine, second derivative is minus sine. So I get a negative sine times f of t, sine lambda x. Look at that, the sine returned. So what's going to happen now? It's going to cancel out, right? It's going to cancel out. And indeed, then I obtain an ODE for my function in time, okay? Now we said there's decay in time, okay? So this must be a function that is decaying. Okay? And decay always brings to mind exponential. And indeed, when you look at this, you have f prime is something times f. The solution to this, so whenever you have a first derivative, you think exponentials. A second derivative, you think sines and cosines, okay? So what's the solution to this is e to the minus k lambda squared t. Okay? So now we plug back into our full solution. Okay? What do we have is phi is equal e to the minus k lambda squared t times sine lambda x. What do you see here? Okay, and the decay, what is the exponent? What is the exponent telling us? Yeah, so the larger the lambda, it squares. So if you have lambda equal 1, it's going to decay at e to the minus kt. If you have lambda equal 2, it's going to decay e to the minus 4 kt. So if I have those two frequencies together, the decay of the higher frequency is going to be faster, because it's going to be e to the minus 4 kt or e to the minus 100 t. The signal we had 10, and then we had lambda was 10, and then another one lambda was 20. So you're exploding the decay rate over here because it's lambda squared. If k is constant, especially, And so this is really cool, right? So this is the proof actually that diffusion operates on the higher the frequency, the faster the decay in diffusion. So when I see this equation, the first thing I think about, okay, it's a sinusoidal in space, it's got a frequency, but that exponential term is a decay term, and the decay is a function of k, but for all problems, if k is the same, the only thing that matters is if the frequency is changing. And it changes e to the minus k squared, e to the minus lambda squared. So there's a lambda squared there, not just lambda. So a frequency of 10 is going to become 100, okay, over here. So it decays it even much faster. Yes?
What happens if we're dealing with, since this is a 1D, I guess, model, what about?
Same solution for 2D and 3D. Same thing. It's just easier to illustrate here, but you can have a crazy signal like that. It will decay in the higher frequency than in the lower frequency. Yeah.
If you have a scenario where you have a lot of sine waves contributing to an initial condition, can you just model it at a few low frequency sine waves to reduce?
No, you just keep the whole thing. But what you can do with this is that if you have a a noisy signal that you obtained from experiments, run it through a diffusion process, one time step, and you smooth out all the high frequencies. You smooth out all the noise. Make sense? So these are what they call Gaussian filters and whatever average filters. It's all coming from this second spatial derivative. If you make this derivative a fourth derivative, the decay is lambda to the power 4, even faster. Okay, so but you'll have a bit wider averaging thing. But that's what diffusion does. So when you go and run this through a filter, an imaging filter or a denoising filter, it's just doing diffusion. What it's doing is just averaging points. It's taking that formula to average the points. Essentially, it's taking a single time step in a diffusion equation. Very simple. Is that cool? Diffusion rules the world. Okay. Similar results are also obtained for cosine. So if you were to put a cosine here, you'll get the same answer. And because this equation is linear, in fact, any linear combination of sines and cosines is also a solution, because the equation is linear. If solution A is a solution to the diffusion equation, linear diffusion equation, solution B is any combination of those two solutions is also a solution, because each one of them satisfies the equation. Derivatives are linear operators. K is constant, so they will all satisfy the equation. You can verify this for yourself. In fact, that this is the general solution for the unsteady diffusion equation. It's a summation of a bunch of signals. Think of this as, it looks ominous. It's not. It's just you're summing up a bunch of sine and cosine waves. We just did it in class. We did it with two sines, right? That's exactly what I did in the notebook. I did 1 times sine 1x plus 0.1 times sine 10x. I just picked two frequencies. Everything else is 0. Then the solution is going to be e to the minus k t sine, etc., plus e to the minus k times 100t on the other signal. Okay. Now, any signal you have, the Gaussian or that heavy side, you can convert that to a Fourier series of sines and cosines. So that will be your initial condition. It will be this, essentially. Your solution when running it in a diffusive process is you're multiplying it by this term. You're multiplying each frequency by that decay term. The higher the frequency, the faster it will decay. Okay? So I have some other animations. Let me dig them out from another course that I teach, which will show you a little bit more. Okay. Let me see. Okay. So this is okay, this is dispersion, never mind. Hold on. Let me see this. Okay, there you go. Okay. This is a signal composed of, if you do the Fourier series of this is what you get. Only 3 frequencies. 1 hertz, the green one, 2 hertz for the red one, so 2 cycles, and 3 hertz for the aqua color one. But you add them together, you get this. Now you run this through diffusion. What you will see here is that the aqua is going to diffuse faster than the red and then faster than the green. Let me show you this. See what happens above? So I'm taking the Fourier series of how my signal is decaying over time, and I'm plotting it, and you see the higher frequencies diffuse faster than the lower frequencies. This higher one is 3 hertz, so that lambda squared is 3 pi squared, right? So, and then it decays faster. Now, you look at this signal. It's got a lot of noise in it, so this is the addition of, 1 hertz, and then I lowered the size of the 2 hertz, 3 hertz, 4 hertz, and like 100 hertz, and then 200 hertz. Okay, so you get to see that noise. Look what happens. In a single step, you clean out all the noise, and then you diffuse the rest. Okay? And then you diffuse the rest. So that's what diffusion does. Cleans out the higher frequency modes much faster than the lower frequency ones. Okay. So again, if I go back to what I said, that sometimes you can get away using central on advection if physical diffusion, if you have a diffusion present, you have a physical diffusion term that's present, and that could essentially diffuse all of these oscillations that you're dealing with. Okay. Next, I want to talk about Newman, and then I'll let you go. We'll implement Newman. We'll review this next week, and we'll implement Newman next week. So Newman conditions are a little harder to work through. Well, they're not harder. They're just, you have to keep thinking about writing an ODE at the boundary points. Okay, so you have to figure out how you formulate that Newman condition as an ODE at the boundary. Okay, so again, I'm taking my diffusion condition, and my standard discretization still is valid. But then for Newman condition, it's given to you as a flux at the boundary, as a derivative at the boundary, normal. And so let's say, at the right-hand side of your domain, I call that x plus phase. So on the plus side of the domain, you have a d phi by dx equal beta. Okay? Now, similar to what we did when we added the ghost cell when we were doing the linear system of equations for the heat equation, we're going to do the same thing here. We're going to do the same thing here, except now I still have a time derivative that I keep track of. So we do the same exact thing. So when we did this problem previously, this was 0. And we just dealt with this equation at the boundary. Right now, this is not 0. It's still d phi by dt. So we just got to do the same change. So if you continue with central, you first discretize your Newman condition, d phi by dx. You assume there's a n plus 1 point, a ghost point, un plus 1 minus, again, you can go back to the slides when we did the ghost points. But this is my ghost point here, assuming a fictitious point that doesn't exist. Un plus 1 minus un minus 1 over 2 delta x, that's centered around n, right? So at x equal L, that's I equal n. And then I can eliminate the ghost point from this. So now my ghost point is 2 beta delta x plus un minus 1. I know beta, so this is known. This is part of the solution that's inside the domain. Then I simply take this and apply it at the boundary. So at n, if I apply my discretization at n, similar exactly to what we did with the linear system of equations. So I have a phi n plus 1, or un plus 1, sorry for the change in nomenclature. I have a phi n plus 1, which is the ghost point, but phi n plus 1 is 2 beta delta x plus un minus 1. I substitute it. It just changes the right-hand side at that one boundary point. For Dirichlet, the right-hand side is 0 or whatever. If the Dirichlet is function of time, you got to figure that out. If it's constant, the right-hand side is 0. But for a Newman condition, this is the right-hand side. And you just simply say, at my boundary point then, at boundary point n, this becomes my equation. So you do the numpy dot roll and everything, and then you go to the right boundary and fix that. The initial condition, you don't touch it. It's not going to matter, because you are setting up the right-hand side here. So you start from 0, okay, or whatever initial state the system was in. Same thing on the other boundary, but if you have at the left boundary, if you have alpha, then there's going to be a sign change over here. But you can do that. Okay, so we'll revisit this on Tuesday. Okay, and then we'll do the same problem, but we're going to put a flux condition now rather than a Dirichlet condition. So I will give you essentially all the possibilities where we can combine Dirichlet and Newman, etc. And this becomes really interesting when we go to 2 dimensions. Okay, it's a little bit more. It's not that much more involved, but you got to figure out the array indexing. But yeah, that covers it. And now you know more than any other first-year grad student knows. I hope. I hope this is all making sense. Sometimes I feel like I'm just talking to myself here, but I hope it's making sense. Something is sinking in, okay? So please review this. I'm not going to come back and re-explain things. Please review this. We're going to be moving steadfast, okay? We're going to be moving ahead. moving on, because my goal is to get to 2D and then do Navier-Stokes. So if you're iffy about anything, is solve IVP, how to go redo all the examples, all the problems, so that you know how to use solve IVP, you know how to use lens space, you know how to use roll, okay? All right, thank you all, Godspeed. I'll see you on Tuesday.